Alright, hello everyone. Today I'm going to be doing a demonstration of this hydrostatics problem presented in the diagram and problem statement that you see here. We have our list of givens as well as a value that we need to solve for, h, the height of the reservoir. So with that, we're going to go ahead and get started by labeling some important points on this diagram, which I'm going to call PO at the top of the reservoir, PB at the same level as point B, the beginning of the gate, and PA, which again, same level, because we know the pressure is going to be the same across that entire horizontal line. So it doesn't matter if we draw it directly on point B or directly on point A. All right, the next thing we're gonna do is we're gonna establish our Z-axis, which is going to be right here, starting at the top of the water level, as is typical, and going in the upwards direction. All right, so now we're going to begin solving for these pressures. So PO at the top of the water, you can see that it's exposed to air, and we're going to go ahead and assume that that is just an atmospheric pressure. And in order to make this problem a lot easier for us overall, we're going to go ahead and assume that the whole problem is to be done in gauge pressures. You're going to get the same answer in the end, whether you use absolute or gauge pressures. So it's just going to simplify the math for us to assume that PATM is 0 kPa in gauge pressures. All right, the next thing we're going to do is solve for PB. And in order to do that, we're going to use the governing equation that we generally use for pressure changes in a body of water, something like that, which looks something like PG, Z, B, in this case, since we're looking at point B. So we have the density times the gravity times the distance downwards into the reservoir itself. Now, we don't actually know what ZB is because this entire height is unknown. That's the variable we're going to be solving for. But we do know our density and we do know our gravity, and we can actually find this height right here because we know the length of this gate and we know the angle at which it's at. So using very basic trigonometry principles, we know that this is equal to 6 sine 30 degrees. That means that in total, this is equal to rho times gravity times h minus 6 sine 30 degrees. All right, and technically this should be this should actually be a whole negative term because our z direction is in the opposite direction. It's going upwards. So we're going to go ahead and remove the negative sign from the front of the equation and simplify it down to rho g h minus 6 sine 30. And that's going to be our equation for the pressure at B. Now, as for the pressure at A, again, we're going to do a very similar equation, PG times ZA. But this one is overall much more simple because the pressure at A is just equal to, or sorry, not the pressure, the height at A is just equal to negative h. So we just end up with rho times g times h. So that one is a lot more simple. Then we're going to go ahead and draw a free body diagram of our gate, which looks something like this. This isn't really to scale. The angle should be a lot steeper, but for our purposes, this will work. So as you know, we're going to draw the distributed load, which tends to look like a trapezoid that we see on these hydrostatics problems at a gate. That's what our distributed load is going to look like. And we know that if this is point B, and this is point A, then this is going to be PB, and this is going to be equal to PA, right? Because the distributed load will increase over time, but we know, or sorry, not over time, over the depth, but we know our minimum at PB and our maximum at PA, which we've already solved for, right? Obviously, there's going to be some reaction forces at the gate, By and Bx, which are kind of arbitrary because when we solve the final problem, we're going to take our moment about that point. So we'll never actually have to solve for these reaction forces in the gate. But you would include them if, for example, the problem asked you to solve for the reaction forces, if that was your unknown variable instead. And then lastly, as mentioned in the problem statement, there's going to be the weight of the gate itself. All right. A couple things to note. We do know the location of where this weight acts because this is a simple rectangular gate. It's always going to act at the center of the gate, which is going to be halfway down the length. Since the length of our gate is 6 feet total, we know that this weight is going to be acting at 3 feet in. So I'm going to go ahead and redraw this, including some helpful labels this time. All right, so this is our weight, and we know that that is acting at about 3 feet in. All right, so the next thing that we're going to do is we're going to try and break this distributed load up into something that's a lot easier to work with and visualize. We want to try and break it down into 2 point loads. So the way we're going to do that is we're going to take this section of the distributed load right here, this triangular section, and we'll treat that as one load, and we're going to take the rectangular section down here and treat that as another separate distributed load, because rectangles and triangles are distributed loads that we can very easily locate the centroid of, whereas with the trapezoid, we're not 100% sure where that might be located. There are some formulas for that we could use, but we're going to try and solve this by breaking it down into parts instead. So let's start with the rectangular one, which I'm just going to call F1 at this point. For any rectangular load, we know, again, it's going to act at the centroid. So it's going to act in the exact same place that this W force acts in. And it's going to go in this direction. You can see the angle. The distributed load acts along the angle of the gate, unlike weight, which acts straight down, as always. And we're going to call this F1. And that's also going to be 3 feet in. And then for the triangular load, we're going to call that F2. And for a triangular load, the load always acts 2/3 along the triangle, closer to whichever side is the maximum. So that is going to act 2/3 along the gate, which we know the gate is 6 feet total, which means F2 right here is going to act at 4 feet along the gate, 2/3 times 6 feet. All right. And then again, as always, we do have the reaction forces of By and Bx. That's point B, and this is point A. Then I haven't drawn it, but obviously this gate is from the problem statement, angled at 30 degrees. All right, so now we're going to go ahead and start solving for what these F1 and force 2 values actually are. So we know that F1 represents the rectangular load, and one of our very basic relations is that force is just pressure times area. So if the pressure at this entire distributed load is held constant at PB, which you can see because this is just the rectangular section, that means the pressure for the entire distributed, that entire distributed pressure is just equal to PB times the area of the gate, which will end up being, as we already solved for PB, P rho times G times H minus 6 sine 30 times the area, which is 6 feet long, and then 5 meters into the page as stated in the, or 5 feet into the page as stated in the problem statement. And I'm neglecting the units in this problem and writing out the answer here for the most part because everything is in standard imperial units. You know, there's no crazy conversions we're going to have to work with. The only thing to keep in mind is that weight as 500 pounds is already a unit of force, so we don't have to multiply it by gravity. But everything else is consistently in feet, pounds, etc. All right, so that's going to be our equation for the first force. Now, the second force is a little bit more complex because it is a triangle. And so the way we're going to solve for that, we're going to solve for P average of A, which is another way of saying the pressure times the area. If you can find the average pressure and multiply it by the area, that's the same thing as finding the pressure across the entire distributed load instead. And so for this triangular shape, you can see that the average pressure will be somewhere pretty much exactly in the middle, actually. And the pressure at that point is going to be equal to 1/2 of the maximum pressure minus the minimum pressure. All right, so that's what we're going to use as our average pressure, right? That makes sense. It's halfway between pressure B and pressure A value. So we're going to go ahead and use that. And so that gives us our force 2 value as 1/2 times PA minus PB times the area, which is, again, 6 times 5 feet. Oh, and my apologies, I forgot to multiply this by our height. And in this case, our height is equal to h. No, sorry. Sorry, I take that back. Just ignore the last 10 seconds. So this is our force equation, 1/2 PA minus PB, 6 times 5. And then we can actually further simplify this because we know how PA and PB are in terms of height, density, and gravity. So if you see that PA is just equal to rho GH minus PB, which is rho GH minus 6 sine 30 degrees, all multiplied by the area, 6 times 5. Then you'll see that if we pull out the constant terms, in this case, rho and G, we'll end up with H minus 6 sine 30 degrees. And as you can see, that will actually simplify very neatly to 1/2 rho G. The H's will cancel, 6 sine 30 degrees times 6 times 5. All right, and I'm actually going to go ahead and simplify both of these 6 times 5 terms into 30. All right, so now that we have these final force values, we're going to go ahead and make our moment diagram, or moment balance equation about the gate. So I'm going to go ahead and copy this free body diagram over so that we can use it while we're building our moment equation. As you can see, we already have pretty much all of the lengths present in the problem. And in order to make this a little bit simpler, we're actually going to do the entire problem on a rotated axis, where this is y prime and this is x prime. And the main reason we're going to do this is just because that's the direction that most of our forces are pointing in. And so it'll make doing the overall moment balance a lot easier. You'll still get the same final answer as if you did it in the typical y-axis. All right. So let's go ahead and figure out how we would translate that W, the weight of the entire gate, in. So we know that this entire gate is angled at 30 degrees. That's given in the problem statement. I know the diagram is not very accurate, but hopefully you get the gist, which means we know that if this has an angle of 30 degrees to the horizontal, then this will have an angle of 30 degrees to our new vertical. All right, so that's how we're going to translate the weight into the new axis system that we have, and I'll go ahead and put the lengths back. All right, so let's go ahead and do our moment balance, which is going to look like the moment about B, because we want to be able to ignore the reaction forces of the gates. There are unknowns that we're not sure about. It doesn't matter because what we're solving for is H anyways. But if you were solving for the reaction forces at that point, then you could take your moment around a different area. All right, so we know that F1 is going to occur at about 3 feet. You can see 3 feet, we have our length, and it's a positive moment because it's going to cause a turn in the counterclockwise direction about the B axis. Then we have our weight, which is acting at the exact same point, but now it's in a negative direction, and we also have to make sure to project it into our new axis system. So we're going to do the weight times cosine 30, and that's going to be in the negative direction, also 3 feet away from the origin in this case. And then lastly, we have F2 acting at 4 feet along the gate. All right, also in the counterclockwise positive direction. And we know that if we want to solve for h at the minimum amount that it would cost for the gate to open, we want to set it equal to 0 because the moment is greater than 0, then we know it's going to start opening. All right? So now that we have our moment equation, we can go ahead and plug in our force values and start solving the problem. So I'm going to go ahead and copy them from up here. We have our force 1 times 3 now because it's in the moment. And again, I'm going to drop the units because everything is currently already in feet. Minus W cosine 30 times 3 feet plus our value of force 2, which we have already written out. Go ahead. And that one's going to be times 4 feet for the moment term that we have, and all of that is going to be equal to 0. All right, so now that we have this, we can go ahead and start plugging in some final numbers. We know that the density is equal to 1.94 slugs per feet cubed. Again, standard units, so I'm not going to write them out. We have the gravity, just known as a constant, 32.2 feet per second squared. We have h minus 6 sine 30, and if you evaluate that, you'll find that 6 sine 30 actually ends up just being 3 times 30 times 3 minus w, which is given in the problem statement to be 500 pounds, or 5,000 pounds, sorry, cosine 30 times 3, plus 1/2, 1.94, density again, gravity 32.2, times 6 sine 30, again, that just simplifies to 3, 30 for the area, and then 4 for the length, the moment arm. And all of that will equal 0. So going ahead to use a calculator to expand that out, we will get 5,622.12 h minus 16,866.36 plus 11,244.24 is equal, sorry, right? So these terms right here are from our force 1. This is force 1. This is force 2. And then we're actually going to go ahead and move the weight onto the opposite side. So you can see that this is a negative term for the weight. So we're going to go ahead and move it, make it positive, and it's going to be on the opposite side of the equation in this case. And that's going to be 1,200 or 12,990.4. All right. You can go ahead and rearrange this to solve for h as the following. All right, and then divided by the constant term in front of h, which is 5622.12. And we're actually going to evaluate that numerically. Get our final answer is h equals 3.31 feet. All right. So that's going to be the minimum height required for this gate to start opening. As you can see, that actually is going to be just slightly above the current height of the gate, because we know that this is 6 sine 30, which is 3 feet total. All right. And in order to double check our final answer and also to kind of practice another method of solving this problem, I'm going to use our given height value, and instead I'm going to solve for the weight. So if our answer for our height is correct, our weight value should come out to be about 5,000 pounds as it was originally given. So we're going to go ahead and bring our free body diagrams back right over here and add our weight arrow. Oopsie. And instead of splitting this into a rectangle like we did, and a rectangle and a triangle like we did in the last part, instead we're going to try and find one specific resultant force and the length at which it occurs, which we're going to call the center of pressure. All right. Remember, so for this resultant trapezoidal force, the center of pressure is not the same thing as the centroid. It's going to be an entirely different thing that we're going to have to calculate. All right. So in order to find the resultant force, in this case Fr, we're going to again use the principle of finding P average, multiplying out by the area. And in this case, we know that P average can generally be broken down into rho times gravity, density times gravity, times the distance to the centroid of our beam, or of our plate, times the area, again, carrying the area over. And in this case, the centroid, which occurs probably just slightly above the center of pressure, we know that occurs, going back to our diagrams again. So if this centroid occurs halfway down, we know that this length right here up to the centroid is equal to 3 sine 30, right? So in total, we have height, and then we know up is 3 sine 30, which means that the distance from the top, or our ZC, is actually going to be equal to h minus 3 sine 30. All right, so let's go ahead and plug that into our equation. This means we'll get rho times g times h minus 3 sine 30, and then times our area again. All right. And in this problem, we're going to, like I said, use the h value that we already have. So let's go ahead and evaluate this numerically, plugging in our density, our gravity, and in this case, h equals 3.31 minus 3 sine 30, which is actually just 1.5. And then times our area, which is, again, 6 feet times 5. And that is going to come out to be about 3,392 pounds. All right? So that's going to be our resultant force. But in order to solve the problem, we need to know the point at which it acts, because we need to take a moment balance around it. In order to find the point that acts at, we're going to go ahead and use this formula where delta Cp, center of pressure, is equal to the moment of inertia with respect to the length, times the centroid, the height of the centroid, times the area, times sine theta, where theta is the angle from the horizontal. And what delta Cp is going to give us is this distance right here that I'm drawing on the free body diagram. That is the distance from the centroid to the center of pressure. And I'm just realizing I forgot to draw the weight, so I'm also going to put that arrow back in there. All right, so let's go ahead and solve for that delta value. So delta Cp is equal to 112 times 6 cubed, because we're going with respect to the length, and 6 is the length, times the width into the page, 5, times Zc, which, as you recall, we already found is h minus 3 sine 30, or 3.31 minus 1.5, times the area, which is also 6 times 5. All right, sine theta, the angle from the horizontal, is 30 degrees. And if you go ahead and plug that into a calculator, you will find that this comes out to be 0.829 feet. All right, which means our actual center of pressure distance is equal to 3, which is the centroid, 3 along the 3 feet along the beam itself, plus 0.829 feet. So we know that this force acts at 3.829 feet along the beam. All right, let's go ahead and take our moment balance and solve the problem. Taking a moment about you, we know that the weight is acting at the centroid, and we know that we have to project it into our new axes, which I'm going to go ahead and redraw up here. And we know this is 30 degrees. Okay, so again, weight times cosine 30 times 3 feet. And then this should actually be a negative term because it's going in the clockwise direction, plus our force resultant, Fr, at Cp, and that should equal 0, which means we end up with, if we're solving for the weight in this problem, we're going to shuffle the terms around, and we're going to get that weight is equal to Fr times Cp over cosine 3 cosine 30, which is going to be equal to 3,392 pounds times 3.829 feet over 3 cosine 30 feet. And evaluating that numerically, we get that the weight is equal to about 4,999 pounds. And you will recall in our original example, the weight was equal to 5,000 pounds. So this is a very accurate approximation, most likely just due to some rounding errors that it's different at all. So with that, we've verified our answer. We know that the minimum height required for this gate to open is going to be 3.31 feet with the gate weighing 5,000 pounds. All right, thank you guys so much.